Hi, this is Raphael Mudge, the creator of Cobalt Strike. Welcome to part 3 of In-memory evasion. So much of this course has focused on how to detect payloads in memory. We detect payloads in memory by looking for anomalies, differences from normal in the properties of the current process, of its threads, and its memory. In part 2 of this course, I wanted to explain and make the case that those anomalies, those differences from normal, are not magic. They are not indicators of intent. They just happen to be byproducts of how some offense tools work in some cases. With that, I can explain evasion in one sentence. Evasion is not doing those things that differ from normal that are used to detect us. And that's what we're going to discuss in this course, or in this lecture, I'm going to start out with evasions in general. We'll talk about Cobalt Strike specific advice, and then I'm going to talk about process context and what you can control there as well. So here are the detections we talked about earlier. We talked about anomalies in the thread start address. We talked about memory permissions and memory content. Let's go through some in general tips for avoiding anomalies in these things. Okay, how do you make your threads look normal? If you control the current process, it is your program, your executable, your DLL. Do not call create thread with an arbitrary pointer. Offensive programs in many places call virtual alloc with liberal permissions. They stick a capability into that new memory and call create thread to kick off the capability. Don't do that. If you can, declare a function that runs your capability and call create thread pointing to that function. That's what normal programs do when they create a thread. That's what you should do in your offense tool set as well. What if you need to create a thread into a remote process? Well, if you can, hijack an existing thread with set thread context. A thread that you happen to take over and resume executing at your capability will still have its original start address, and that will get you past some of the heuristics we've discussed. Another option is to drop a capability to disk and call load library via create remote thread. If you use load library to get your capability into a process's memory space, it is going to look like a DLL loaded normal way. And of course, DLL hijacking and friends are options as well. So those are some options to make your threads look good. What about memory permissions? RWX permissions do occur in limited amounts of legitimate use. But remember, the observable properties of memory permissions include the initial state of the memory and the current state. And initial RWX permissions and current RWX permissions are a big indicator. Avoid these. What's the solution? Map page permissions to something plausible. In some cases, avoiding RWX is enough, but consider things like using map view a file to map a DLL into the current process space and overwrite its memory. Using things like map view a file give you access to memory permission options that you don't have with virtual alloc. Let's do some evasion tips related to memory content. Tip number 1. Don't look like a DLL unless a DLL is expected. If you're overwriting memory space where a DLL is expected to be located, Sure, look like a DLL. Otherwise, don't. Get rid of those. This program cannot be run in DOS mode strings. Get rid of that MZ header and other indicators of a DLL. If you're aware that analysts are using a certain string or indicator from your tool set, obfuscate it or remove it. Another thing, there's a POC called Gargoyle, and what it demonstrates is the ability to encrypt or obfuscate the memory of a program when most of the program is sleeping. So if you have that kind of capability, obfuscate your memory when your capability is not actively in use, so it's harder to observe you by your content. That sounds like magic dust, doesn't it? Like, hey, just encrypt your memory. I wish it were that easy. Honestly, I do. But I'm just pointing out that that is an option and a place where we'll probably see offense tool sets go for dealing with these kinds of analysis. Now that we've talked about evasions in general, let's apply these concepts to Cobalt Strike use. For your threads, the executable and DLL artifacts are okay. I took care to try to do closer to the right things in the default artifact kit. Beacon's process hollowing, at least when it's executed from a 64-bit beacon on a 64-bit system, is okay. I do use set thread context to hijack the main thread of the temporary process. I do recommend that you avoid injecting into existing remote processes. Beacon does use things like create remote thread and a few alternatives if that fails to execute code in an existing process when it needs to do so. Memory permissions. Avoid artifacts that use RWX permissions. I do have a chart in the last lecture. It's going to come up again in this one, so be aware of that. I recommend that you avoid the use of stagers. Payload stagers use RWX permissions because they expect to receive an encoded payload that decodes itself in place. If you avoid stagers, you avoid the negative permissions there. I also recommend that you set the use RWX option in your malleable C2 profile to false. This will change how Beacon's reflective loader sets the permissions on the Beacon DLL once it's initialized in memory. As you'll remember in part 2, I kept saying, and the Beacon DLL initiates itself and uses RWX permissions. Well, you can turn that off, and the use RWX option in your malleable C2 profile is how you do it. This is a good point to introduce what you can and can't control via malleable C2 profile. Cobalt Strike 3.7 introduced a technology called malleable PE. And this is a set of extensions to malleable C2 to modify Beacon's reflective DLL. What can you do? You can add data to the end of the Beacon DLL and to the beginning. You can replace arbitrary strings within the Beacon DLL. Be careful with this because you could break the functionality of the payload if you do this recklessly. But used carefully, this is a powerful tool. You can add arbitrary strings to the Beacon DLL. You can also manipulate several of the P header fields, which influence how the Beacon DLL loads itself. And you can set some hints within the Beacon DLL that its loader uses to enable certain kinds of obfuscations. For example, turning off the use of RWX permissions is one of those obfuscations. Here's an example of a malleable PE block from a Beacon Malleable C2 profile. This one is not that bad. It uses use_RWX to tell the Beacon reflective loader to not use RWX pages by setting that option to false. We changed the size of the chunk of memory Beacon's DLL allocates for itself from its default of, I can't remember, 260 kilobytes or so to 512 kilobytes. We take advantage of transform x86 to prepend NOP instructions to the beginning of the DLL, and we get rid of the known string reflective loader and change it to do legit stuff. So that's an example of a malleable PE segment of a malleable C2 profile. Now that we know what malleable PE can do, let's talk about memory content evasions. I recommend that you use the prepend directive to offset Beacon's DLL in memory. Why? Many automated solutions and tools to detect DLLs in memory do not do a linear byte-by-byte scan of memory looking for a PE file from all those locations. It's very expensive to do that. Instead, they look for a DLL at different boundaries, like the beginning of a page or the beginning of a region of allocated pages. If you use the prepend directive and offset Beacon's DLL with instructions that do nothing, you will defeat some of these technologies that are designed to detect a DLL in memory and either flag an alert or deny an action. Take advantage of the string replace directive to get rid of known strings. There are a lot of known strings in Beacon's DLL that I, your vendor, am going to do nothing about. I promise. Reflective loader. You don't need it. Get rid of it. There are heuristics. Actually, it's not heuristics. It's a plain out signature for Stephen Fewer's, for projects that use Stephen Fewer's reflective loader function. Just get rid of it. You don't need the reflective loader string in your Beacon's memory. You also do not need strings like this program cannot be run in DOS mode. So get rid of the things that are of concern. Finally, if you are interested in trying to hide your presence as best as possible and reduce what people can look at to find you, take advantage of the obfuscate directive. This directive in Malleable C2 masks the import table in Beacon's DLL and the section headers. So in effect, the functions Beacon imports and the libraries it load don't appear in memory in plain text at all if you enable this directive. So that's a way of reducing some of the things a person might see if they're looking for Beacon. Now that we have some tips to use Cobalt Strike without running afoul of these in-memory detections, let's talk about OPSEC review. This is a step I recommend you undergo before you use a new payload configuration on a target. Here's how to do it. First, export your Beacon DLL file. Go to Attacks, Packages, Windows Executable S. Don't choose DLL, choose RAW. The DLL option will give you the Artifact Kit's version of a DLL. RAW will give you Beacon's reflective DLL with the modifications from your profile applied to it. Press Generate. Save this Beacon file somewhere. You can use the strings command to look for the plain text strings visible in the Beacon DLL file. You can use strings-EL to pull the wide character strings from the Beacon DLL. And if you want to verify that your prepended bytes are there and kind of just see the plain text strings in the P header, use the hex dump command with the -C option for canonical view. All right, let's take a look at the OPSEC review and what it looks like after we apply some of these changes to the beacon payload. Here we are in Cobalt Strike. This is the licensed version. Let's go to Attacks, Packages, Windows Executable S to export the stageless payload. We're going to choose the raw option because that's going to give us the self-bootstrapping, position-independent beacon DLL blob. Let's go ahead and save that. And let's run strings on it real quick. And here you can see the strings associated with the library's beacon loads and the functions it imports. And you'll see some strings, if we scroll up, associated with beacon itself. Okay? And for completeness, let's run the strings command and pull out any wide character strings. Oops, not -B, -E. -E for encoding, and we're going to do 16-bit Little Endian encoding. And these are the wide character strings embedded inside of the beacon DLL as well. These are pretty standard. Making sense so far? And let's take a look at all of this with hexdump. Do a hexdump-c beacon.bin. Pipe that to more. And here you can see a DLL. We've got the MZ header right there. Got this program cannot be run in DOS mode. You've got the label for the text label for a section. So some dead giveaways of a PE right here just in these first bytes. That's what we're looking at by default. Okay? Not so good. Now let's go ahead and make a few changes to a malleable C2 profile. I'm going to work from my favorite profile, which happens to be the web bug. And let's do a stage block. We'll do set use RWX to false, right? Let's set the image size x86 to 512 kilobytes. Let's set obfuscate to true. And let's transform the beacon in a few ways. Let's get rid of the reflective loader. We'll just replace that with nothing. And by the way, when you string rep with a different length string, it will just pad the replacement string to match, so you won't mess anything up. What else do I want to get rid of? This program, getting rid of that. This program cannot be run in DOS mode bit. This program cannot be run in DOS mode. Seems good to me. And if I recall correctly, there should be a beacon.dll string in the strings for our beacons. Let's search for that. Grab beacon. Yep, beacon.dll. Let's get rid of that. So that's getting rid of a few strings we might not want. And let's prepend our beacon stage with 2 not bytes. So 90 is the no op instruction. So got 2 instructions that do nothing. I think that's good to demonstrate our purposes. Let's go ahead and take a look at this with C2lint. You should always test your profiles with C2lint, because you might make a typo like I did here. I did STT rep instead of string rep. One is not like the other. And let's try it out. And C2lint is not complaining. I'll take that as a positive. So let's go ahead and start the team server. and let's point to our WebBug profile that happens to have this malleable P block. Let's go ahead and start up the Cobalt Strike client. Same thing. We're going to export our ready to self-bootstrap almost position independent blob. I should say that because one thing is different, and that is when Cobalt Strike deploys the beacon DLL, it does prepend a stub to jump to that reflective loader and give it a pointer to the beacon in memory. That stub is not present in this raw blob, but everything else is. All right, so got that. Let's save that as beacon.bin. And let's take a look at some things. So let's do strings beacon.bin. Pipe that to more. And what I want you to take away from this is the strings associated with the import table are gone. There are some strings associated with beacon, which we can get rid of with string rep, but the actual import table is gone. It's no longer present. And if we take a look at, let's see, grep for this program, not seeing this program cannot be run in DOS mode. Let's grep for the reflective loader, grep for beacon. All those things are gone. Good. There should be no change to the 16-bit string, or 16-bit strings, the wide character strings. Those are all still there. No big deal. All right, let's take a look at this with hex dump just to briefly review the structure of the file, the first few bytes. And what you can see, there's our null bytes, our 9090, our NOP instructions. And there's the MZ header, offset, right? And this program cannot be run in DOS mode is gone. The .text section header piece is gone. So now you got something that could still be seen as a DLL if somebody's very careful with their program, but there's some obfuscation there. So that's a pretty good step, I think. All right. Now, let's go ahead and run this file on target. Let's go to text, packages, Windows executable, and we'll do an executable, Windows exe. Hit generate. Let's save this. Beacon.exe. We're going to host it, and we're going to host it as safe.exe. Launch. Let's go run this on our test target. Let's open up Internet Explorer. We're just going to run our beacon.exe. And let's go ahead and look at Process Hacker. It's going to run as an administrator. And by now, you should know what it looks like to look at Beacon and Process Hacker. Let's take a look at this safe.exe, which we've decided to run. We did nothing to disguise the process characteristics, so who cares there? Threads. This is more the responsibility of the artifact, but the threads are okay. Let's look at the memory. And there are no read, write, execute pages here, right? And if we want to go looking for beacon, you got to kind of dig a little bit. We know it's 512 kilobytes is the size of the region it allocated for itself. And so you have to jump around a little bit to try to find where's our beacon DLL in this particular process. Oops, not there. So it's a lot of fun when you make some changes and try to find yourself. You're like, okay, well, I guess it's a little bit harder. One of the reasons it's a little bit harder in this case is because The beacon DLL is actually not in a contiguous region, all with the same permissions. The different sections of the beacon DLL have different permissions. So process hackers actually separated them out, which makes things a little bit harder. So that's good. That's what we want. We want it to be harder. We know what we're looking for, and it's harder now. So that's an example of how you can change some of the characteristics of what the beacon DLL looks like in memory using malleable PE, and how to check these characteristics prior to your operation just by doing a quick OPSEC check. This course began by describing memory detections as looking for known anomalies in the properties of processes, threads, and memory. I didn't say much, though, about detections applied to your process context. There's a reason for that. The properties of your process itself aren't really what are getting you caught, but the properties of your process and its parent, its process tree, do make a big difference in how some automated solutions and even analysts view your activity. The same set of indicators are not treated equally across all process contexts and process trees. More credible process contexts and process trees are treated differently in some cases. Here's a few things. If your DLL or executable is signed with a valid digital signature from a trusted entity, that's going to buy you some leeway. Having a safe, plausible parent process will buy you some leeway. There's a big difference between Explorer.exe running CMD.exe and MSWord.exe doing it. Also, I recommend, where you rely on temporary processes, do not use processes normally seen in offense activity. For example, Rundle32. Sure, it's signed with a valid digital signature from a trusted entity. It is also the favorite whipping boy of offense tool sets. So don't use Rundle32 anywhere. I have to have some sort of default. I may as well make it a lousy one, right? Because my default is by definition going to be lousy, but you control it. Don't use Rundle32, use something else. So one way to get the process tree right during your use of Cobalt Strike is to take advantage of something called session prepping. Session prepping is changing how the beacon payloads spawns its processes. It's pretty simple. First, use the PS command that just uses APIs, it does not run a program. Use the PS command to survey the processes on the current target. You can use the ppid command to anchor all programs that beacon runs to a specific parent process. So for example, if you happen to live in a user context, anchoring to Explorer.exe is a good idea. If you happen to live in a system level context, anchoring to something that fits there is a good idea. Beacon does spawn temporary processes for many of its post-exploitation tasks. Use the spawn2 command to change which program it spawns. Make it something plausible for the situation. I'll give you an example. I was side saddling with one of the guys from Spectre Ops earlier last year. And he was working an engagement with a pretty good endpoint solution. And he was trying to run PowerPick, which is the capability in Cobalt Strike to run PowerShell without PowerShell.exe. And it wasn't working. The technology on this target was denying the action. And he didn't session prep, though. So what we ended up doing is taking advantage of ppid to anchor to explorer.exe and change spawn to something plausible like iexplorer.exe, and voila, the action suddenly allowed. Session prepping can make a big difference in what is given a free pass and what is stopped. The other thing, the context your payload lives in when it gets on target is heavily influenced by the artifact that put it there, especially the thread. The artifact completely influences that. So here's that chart from the last lecture of the OPSEC characteristics of the various artifacts in Cobalt Strike. I recommend that you stay aware of these characteristics as they are, but I highly encourage you take advantage of the flexibility in Cobalt Strike and modify these artifacts to do things that are more OPSEC safe. Change the PowerShell templates and make it so you have better characteristics based on the things I discussed in this presentation. You can do that. That flexibility is in your hands. For Cobalt Strike users, I summarized my evasion advice here. First, take advantage of what Malleable PE gives you. This is your opportunity to change the beacon payload and change the indicators of how beacon sits in memory. Next, I recommend you do an OPSEC review prior to your engagement. Test your configuration, verify everything looks as you would expect. Export a raw payload, do that static analysis on it. Run that payload in a virtual machine. Check your artifact. Make sure you don't have threads that are not backed by a module. Make sure you're not dealing with RWX permissions. You can do that with Process Hacker. When you're using Cobalt Strike, use OPSEC safe artifacts. Avoid payload stagers. Operate stageless if you can. Take advantage of session prepping to make your process tree look better, especially for temporary processes that house beacons post-exploitation jobs. Finally, limit your post-exploitation actions to ones that your team has deemed OPSEC safe for the environment you're dealing with. Well, it looks like we're at the end of the evasion lecture. In part 3 of this course, I discussed evasion in general, how to do things in a more normal way that don't create the anomalies that these memory detection heuristics look for. I took you through your options to use Cobalt Strike in a way that is better when these types of memory detections are present. I also explained how to influence your process context so that when you're performing offensive actions, you are doing so from a more plausible process tree. This is a big deal because the process context you're in determines how high of a threshold your actions need to pass before they're considered malicious by an automated solution. So good session prepping, good process context can buy you a lot. This concludes part 3 of In-Memory Evasion.